It's great to be back in New York. I grew up in New York. I went to Columbia, so this is home. And thank you all for coming. Today, I'm going to be talking about APIs. This is very much not a typical Josh talk. Anyone who has seen me talk before knows that usually, I've got code on every slide, and usually a lot of it's Java code. This talk has only one slide with code, and it's 70-year-old assembly language. It's not actually a brief talk. Let's see, I gotta look at the clock. Yeah, so I've got 41 minutes to do it, and it was originally an hour talk. We'll see how it goes. APIs. A while ago, some guy asked me, hey, how did APIs develop in the history of programming? Okay, so it was a federal judge who asked me, in this interrogatory in the Oracle v. Google trial, but you have to admit, it's a great question, right? I answered it as best I could at the time, but I realized, this is a piece of history, and I don't really know the answer, and I studied it, and the result is this talk. The talk is divided into three parts. The first two directly answer the judge's question, and the last one is a discussion of the current legal status of APIs and how it affects all of us in the software field. So, first, let's talk about who invented a subroutine library, because you can't have APIs without subroutine libraries. So the term first appeared in Goldstein and von Neumann's Planning and Coding of Problems for an Electronic Computing Instrument from the Institute for Advanced Study at Princeton in 1948. And that's before any general purpose computers had ever been built. It's the first account of programming methodology as people all over the country were preparing, all over the world, were preparing to build computers after World War II. And this report basically made its way to all the labs that were trying to build computers, and it was enormously influential. And it does contain this key idea that most programs will make use of common operations, and a library of subroutines reduces the amount of new code you'll have to write when you're writing a program, and also it makes it much more likely that the program will be free of bugs, right? Because you're using tried and tested code. And here it is in black and previously white, and you probably can't read all this stuff, but simple and composite problems, routines and subroutines, changes required when using subroutines, they were all over subroutines in here. So it seems that Goldstein and von Neumann invented the subroutine library, right? Case closed. Except the ACM would beg to differ, because in 1967, the second ever Turing Award, let's try that again. The second ever Turing Award was awarded to Morris V. Wilks, and the award says, he is also known as the author, with Wheeler and Gill, of a volume on preparation of programs for electronic digital computers in 1951, in which program libraries were effectively introduced. So the second ever Turing Award was given to Wilks for introducing subroutine libraries. What gives? Why didn't Goldstein and von Neumann get the award if they invented it? Well, the answer is pretty simple, actually. They were peddling vaporware. It's true. So it turns out that Martin Campbell Kelly wrote a lovely history of the first few years of programming called From Theory to Practice, The Invention of Programming, 1947 to 1951. And in it he said, Goldstein and von Neumann's preparatory routine would have required extensive operator intervention, and it is difficult to imagine that it would ever have worked in practice. In other words, to get a program that used subroutines to actually work would have, each time you ran the program, involved a lot of work on the part of the person who fed the program to the computer, and it just, it was impractical. It was like they had this idea, but they didn't know how to make it work. But Wilks and Wheeler's idea was the real thing, and here it is. They built a computer called EDSAC at the University of Cambridge Mathematical Laboratory. And I'll give you a few of the vital stats on EDSAC. It was the world's first functioning stored programming computer. It came to life on May 6, 1949, and it was immediately useful as a research tool throughout the university. It ran 650 instructions or orders as they were known, per second, blisteringly fast, right? 650 instructions per second. Initially, it had 512 whole words of memory. Eventually, they expanded that to a K, and they were 17-bit words. Don't ask why. I do know, but you don't want to. And the memory was stored in ultrasonic mercury delay lines. There were these big tanks of mercury, and vibrations would go through the tanks and then be reapplied at the other end, and you would just sort of keep the mercury moving to keep the bits in memory. It's finicky technology and also a little bit dangerous. Input was paper tape. The output was a teleprinter. It ran at a blistering 6 2/3 characters per second. So, never complain about your network speeds, because that's what they had to put up with then. It used 3,000 vacuum tubes. It used 12 kilowatts of power, and it occupied an entire 15 by 12 room. So in round numbers, the thing was, I guess, 4 million times slower than a modern PC. It had 4 million times less memory than a modern PC. It used 1,000 times the power, and it was it used 100 times the power, and it was 1,000 times the size. So, it was a monster and a pig, but it was like, it changed the world. The name EDSAC is an homage, the name EDVAC. Yeah, EDSAC is an homage to EDVAC. EDVAC is the machine that Goldstein and von Neumann were working on, and they didn't finish it until 1951, 3 years later, and it only worked on a limited basis initially. So what gives? Given that the Americans had a 2-year head start over the Cambridge team, why did the Cambridge team finish their machine so much faster? Well, in a word, simplicity. He kept it simple. Once again, quoting from Campbell Kelly's book, the reason for the rapid completion, which was well ahead of any American computer, was that Wilkes wanted to have a machine as practical computing instrument rather than a machine of the highest technological performance. So, first you make it work, then you make it fast. To this end, he kept the EDSAC simple, conservative in electronics, and conventional in its architecture. And then Andrew Herbert, who led a project to restore the EDSAC and make it work again recently, said, he added that the refinements came later. The sequence of diagrams over the next 5 years shows that after they got it running, they did all sorts of stuff to make it faster. But they kept it simple and got it running and put it into production right away. And by 1948, they were able to do this. Here's the first program that was ever run on EDSAC. Actually, I don't have the program on the slide, but this is the actual note from the lab notebook, and it says, machine in operation for the first time, May 6th, 1949. Printed table of squares, 0 to 99. Time for program, 2 minutes and 35 seconds. But that was fast, because how did you do a table of squares before that? You did it by hand or with a mechanical calculator. So, it would have been half an hour's work. So this was, it was earth-shattering at the time. The second program, which was, written just a few days later, printed the first 170 primes, and it was written by Morris Wilkes himself. The first one was written by his PhD student, whose name was David Wheeler. Simple toy programs like that didn't need much in the way of an architecture. They didn't need subroutine libraries. So the architecture was just a simple set of initial orders, which in modern terminology would be called a bootloader. And it was stored on an electromechanical telephone switch. The whole machine was electronic, except this switch, which contained the bootloader. And it simply read the program off the paper tape, put it into the mercury delay lines, and then started execution at the location immediately following the bootloader. The bootloader took up the first 30 words and by the way, you would press a button like on the console, and it would copy the first 30 words, the bootloader, from the phone switch into the mercury delay lines, run it to read in the tape, and then continue running the program that was read in from the tape. Simple, right? It turns out that, technically speaking, I suppose, the initial orders were an assembler because the tape did not contain binary code. Wheeler and Wilks knew that humans would be making these tapes, and they wanted the machine to be kind of human-centric, so they decreed that humans could always program in assembly language, sort of mnemonic codes, rather than actual binary. So you never actually had to use the binary. And Wheeler wrote the initial orders. They worked as far as they went. But just a few months later, Wilks tried to write his first real program. And here's a little quote from Wilks' memoirs. Here's what he had to say about it. By June 1949, I was trying to get working my first non-trivial program, which was for the numerical integration of Airy's differential equation. He was a radar engineer in the war, and he was a physicist, and he did computations of waves bouncing in the ionosphere, and this differential equation apparently tells you about that. So it was on one of my journeys between the EDSAC room and the punching equipment that, hesitating at the angles of the stairs, the realization came over me that a good part of the remainder of my life was going to be spent finding errors in my own programs. This is the first program ever written on the first computer ever built. That's amazingly deep insight, given that this guy was doing something entirely new. But I think we all know that he was absolutely right. But Wilks did see high-quality subroutine libraries as a partial fix for this problem. He thought, basically, if you don't have to debug every little thing because you can rely on a library of high-quality code, then it'll be at least a bit easier to write correct, efficient code. So he gave the task to his PhD student, who was David Wheeler. And Wheeler's architecture for subroutines was finished. He basically spent the summer writing it, so he finished it that September. And he added what he called coordinating orders to these initial orders. When you hear order, think instruction. So what he did was he added sort of fake opcodes, which were instructions not to the computer, but to the compiler, that is, to the initial orders, sort of telling you, hey, this subroutine is being relocated here, hey, we're invoking this subroutine here, and doing parameter passing, all the things that you have to do to basically invoke subroutines from code. And his system was a masterpiece. It required no manual intervention whatsoever. The program consisted, as it says, of the main program, kind of intermixed with these coordinating orders, followed by the subroutines, all on a single tape. And this magic little program that made it all work was only 42 instructions long, which, given that the simple bootloader was 30 instructions, is amazing. Like, how did he do this and why? Well, he did it by working very, very hard, and he did it because he had no choice. He was constrained by the size of the phone switch, right? He only had 42 instructions to work with, so he did the best that he could using those 42 instructions. And Wilks, his advisor, who was generally not prone to overstatement, described it as a tour de force of ingenuity. And you can actually read this code in a book that I'll discuss later if you're curious. Here is Wheeler's subroutine linkage technique called the Wheeler jump. I'm not going to discuss it in any detail because I don't have time, but I will tell you a couple things about it. First of all, it did allow for subroutines to call other subroutines to arbitrary depth, which may sound like an obvious thing to do, but who here has programmed the BASIC language? Anyone? Yeah, BASIC doesn't let you do it. Go sub before return in line 37. That was an error message. So it did not allow for recursion. A method could not call itself. That didn't become possible until basically a decade later in Algol and Lisp. It did allow for higher order functions. You could pass a function to a function because when they were designing this, they knew they were going to want to solve differential equations and do numerical integration. And in order to do that, you have to pass functions to functions. So it was an amazing piece of work for its time. It's overly tricky by modern standards. It turns out this is self-modifying code. Now that would be a security nightmare, but at the time, it was a clever solution to a difficult problem. Here's what the EDSAC subroutine library itself looked like. Sorry, I keep hitting the wrong button. Anyway, it was, in fact, a library. See, here it is in this little thing. Each drawer contains a bunch of tapes. You know, the top one contains arithmetic subroutines. The next one is complex arithmetic subroutines. And this woman here is the computer operator, and she basically takes the tapes of the main programs and the tapes of the subroutines, and using automatic punching equipment kind of combines them into a single tape that's then going to be fed to the computer. And here's another view of the EDSAC subroutine library. This is kind of a logical view, and it contains kind of the labels on each drawer: floating point arithmetic, complex arithmetic, debugging, division, exponentials, functions, differential equations, special functions, power series, logarithms, miscellaneous, print and layout, which is output, quadrature, which is you know, numerical integration, input, nth root, trig functions, counting operations, vectors, and matrices. What an astonishing amount of coverage for the first subroutine library ever written, and the whole thing was written, you know, in under a year by a tiny little team of, you know, one professor and a few graduate students. This is the book that introduced subroutine libraries to the world. It's got a long name, The Preparation of Programs for an Electronic Digital Computer, with reference to EDSAC and the use of a library of subroutines. So they knew right up front that the subroutine library was the most important thing in this book, and they put it in the title. This was the world's first text on programming. This was it. And for the next decade, it was like the only text on programming. It was, you know, as important as any programming book is now, though it is largely forgotten in this era. It was known as WWG back then, in the same way as we call the Kernahan and Ritchie book on the C programming language KNR now. You know, this was it. This was the bomb. This was the book on programming for basically the rest of the 1950s. And it wasn't really supplanted until sort of higher, you know, programming languages like Fortran became the order of the day in the late 1950s. Wheeler presented the key ideas from this book and the related research in a 1952 paper at what would become Carnegie Mellon University in Pittsburgh. And the paper described all of these concepts: the subroutine library, generality versus performance trade-offs in designing subroutine libraries, the importance and difficulty of documenting a library, information hiding, dynamic debuggers, and higher order functions. And the astonishing thing is they built all of these things. You know, this wasn't just, these are things we might do. These are what they had done in the past couple years. Here's a remarkable passage from the paper that I'm going to read to you in its entirety. It should be pointed out that the preparation of a library of subroutines requires considerable amount of effort. This is much greater than the effort merely required to code the subroutine in its simplest form. It will usually be necessary to code it in the library standard form, and this may detract from its efficiency in time and space. It may be desirable to code it in such a manner that the operation is generalized to some extent. However, even after it has been coded and tested, there still remains the considerable task of writing a description so that people not acquainted with the interior coding can nevertheless use it easily. This last task may be the most difficult. This was in 1952. You know, it's just amazing to me how much they knew back then. 42 years later, David Parnas wrote this. He said, "Reuse is something that is far easier to say than to do. Doing it requires both good design and very good documentation. Even when we see good design, which is still infrequently, we won't see the components reused without good documentation." And that was still news to everybody in 1994, you know, even though it's precisely what Wheeler said in 1952. Here's another remarkable passage. This is the conclusion of the paper. He says, "The primary objectives to be borne in mind when constructing subroutine libraries are simplicity of use, correctness of codes, and accuracy of description. All complexities should, if possible, be buried out of sight." There's a lot going on in that one sentence. Here's something that I wrote in 2006 at an UPSLA keynote called How to Design a Good API and Why It Matters. APIs should be easy to use and hard to misuse. It should be easy to do simple things, possible to do complex things, and impossible, or at least difficult, to do wrong things. Documentation matters. No matter how good an API, it won't get used without good documentation. Minimize accessibility. When in doubt, make it private. So those are exactly the same ideas that were in the conclusion of this 1952 paper. And in addition to its prescient wisdom, there's one more truly remarkable thing about this paper. It was only 2 pages long. That's it. This is the whole paper. And by the way, I found a typo in it. But, you know, I stand in awe of this paper. The amount of material that he was able to cram into these 2 pages is truly remarkable. And almost all of it is still of value today. I'll post a link to the PDF in case you guys want to read it. I recommend that you do. It's good reading. So at this point, I think it's safe to say that we know who the inventors of the subroutine library are. The primary inventor is David Wheeler, and you know, I think there's little doubt. But what about APIs as opposed to subroutine libraries? Why didn't Wilson Wheeler discuss APIs as a separate entity? Well, basically because in those days, the 2 things, a subroutine library and an API, were isomorphic. You know, there was only one machine architecture because this was the first machine ever built. And in fact, there was only one machine because this was the first machine ever built. So the notion of portability didn't exist. You know, it's not like you would take a program written on one system and run it on another system with the same API. You know, and there were no legacy programs because there were no programs. The notion of backward compatibility didn't exist because backward compatible with what? So there was basically no reason for them to discuss the API separately from the library. They were one and the same back in those days. But I think it's clear from that 2-page paper that Wheeler wrote that they really did understand quite well the principles of API design even back before they'd come up with the notion of an API as a freestanding entity. The field progressed, and then existing subroutine libraries had to be re-implemented. Why? Well, new hardware was built, like they did a new version of the EDSAC machine, and they basically, you know, ported the old libraries to the new machine to run more quickly using the new instructions on the new machine. And new algorithms were devised, so you could take the old APIs and, you know, do things like matrix multiplication faster using new algorithms for matrix multiplication, and so on. And these things gave life to APIs independent of the underlying subroutine libraries. You know, as soon as you start re-implementing an API, then the API is a separate thing from the library. It isn't just sort of your view into the library. As far as the term API, I don't think we started using it until 1968. And this represents independent research on my part. You know, when I looked it up, like a couple of years ago, Webster said the term came from, you know, the late 70s. And I said, that can't be possible. And I did a literature search. This was the earliest paper that I could find that actually used the term. It's called Data Structures and Techniques for Remote Computer Graphics, and it's by Ira Cotton and Frank Greatorex. And I actually went and talked to Ira Cotton. Frank is no longer alive. Ira was a student of, I forget. Anyway, I talked to Ira, and I said, you know, hey, did you guys come up with the term API? And he said, no, we didn't, no. And I said, but it's mentioned in this 1968 paper. And he said, oh, is it? Well, let me see. You know, yeah, I guess we came up with it. And I told Merriam-Webster, and now 1968 is listed as their earliest citation. So this is the first use of the term. Let's go a little deeper into what this paper has to say. First, it dances around the term. It says, normally the interface between application program, so there you go, application program interface, and the system is desired via Fortran-type subroutine calls. Okay. Then they say, the system has been designed to be essentially hardware independent in the sense that the implementation may be recoded for different or improved hardware while still maintaining the same interface with each other and with the application program. So there's the concept clearly defined and motivated. And then they run with the term. A little further in the paper, it says, finally, hardware independence at the central computer means that a consistent application program interface could be maintained if the program were replaced. Eventual replacement of at least a portion of the hardware is almost a certainty given the rapid rate of new developments in computer technology. This was in 1968, by the way. They had no idea what was ahead of them, but they were absolutely right. Then they say a sufficiently flexible hardware-independent system guarantees that technological advances will not make the system prematurely obsolete. So it's key that they understand the value proposition of APIs, that APIs represent the glue which allows you to put a new implementation of a library underneath existing code so that you keep the value in that code and in your knowledge of the API. So what's going on? The authors understood the underlying concept, and that the API had a life of its own apart from the library. And once you have this sort of freestanding entity different from the library, it deserves a name. And the name they gave it was Application Programming Interface, or actually Application Program Interface. The ing got added later. Many other people understood it too. It's not like this was some sort of great intellectual achievement that they came up with this name. It just sort of naturally arose. So in summary, libraries naturally give rise to APIs. APIs weren't invented so much as they were discovered. So I would claim that Wheeler and Wilkins latently invented the API in 1948, and it just took us another 20 years for us to discover it and give it a name. All right, that ends the first part of the talk. And the second part is devoted to what exactly constitutes an API. As of April, this is what Wikipedia said. A set of subroutine definitions, protocols, and tools for building application software. In general terms, a set of clearly defined methods of communication between various software components. And I think that's not a bad definition as far as it goes. It's actually a lot better than the definition they had last year. I would quibble with the three things in red. I don't think tools are part of the API. I think they're an adjunct to the API. I wouldn't limit it to building application software. You build system software with APIs as well. And they say that it's used to communicate between software components. As you'll see later in this section, I believe APIs are also used to communicate with hardware components. The purpose is described, and this is my paraphrasing, as to define a set of functionalities independent of their implementation, allowing implementation to vary without compromising the users of the component. And this definition gives rise to a two-part test for whether something's an API or not. If you can answer yes to both of these questions, it's an API. Does it provide a set of operations defined by their inputs and outputs? And does it admit reimplementation without compromising its users? If you can say yes to both of those things, then you probably have an API on your hands. So now let's take a whirlwind chronological tour of 12 reasonably important APIs of the past 50 years. The first one that I'm going to discuss is the Fortran Standard Library. In 1958, when Fortran 2 came out, it came out with 28 math functions, and they're all listed in this table here. This is the Fortran Standard Library, and astonishingly, it still works. If you write a Fortran program today using these library functions, it will still run. So APIs kind of last forever. Notice, by the way, that I have kind of the API shown in this picture, and I have the underlying architecture, which is Fortran, shown in this picture. I'm going to stick to that convention for the entire whirlwind tour. Here's another thing that may be an API. The IBM S360 instruction set, which came out in 1964, and was how programmers communicated assembly language programs to the IBM computer. It is summarized on this famous green card, and it ran on the IBM 360 architecture. It was subsequently re-implemented on other larger IBM 360s, and then on IBM 370s, and on clone machines by companies like Amdahl. The whole mainframe industry formed around this API. Do you guys think an instruction set is an API? There's some disagreement as to whether it is or not. Show of hands. Is this an API? Yeah, about half of you say it's an API. It feels like an API to me. Then another one is the C standard library in 1975, and it's really fundamentally no different from the Fortran standard library. It's bigger because C was a bigger, richer language, and it just did more things. But it's still not huge, and it is not fundamentally different. Here's an interesting discussion of the library from K&R's C book. They clearly understood the role of APIs in ensuring portability. It says, input and output facilities are not part of the C language. Nonetheless, real programs do interact with their environment. In this chapter, we describe the standard I/O library, a set of functions designed to provide a standard I/O programming interface. The routines are meant to be portable in the sense that they will exist in compatible form on any system where C exists, and that the programs which confine their system interactions to facilities provided by the standard library can be moved from one system to another, essentially without change. So, there you have it. What they're saying in that last sentence is essentially the same thing Sun said when they said, write once, run anywhere. They just didn't have the snappy marketing department, but it's the same thing. So you could move the program from one computer to another without change because you've got an API. Also, they clearly understood that core APIs are inseparable from the underlying language. They kind of said, yeah, technically, the standard library isn't part of C, but it's going to be implemented everywhere that C is. Another kind of API is the API between programs and the underlying operating system kernel. So here's the Unix system calls. This happens to be from the 6th edition, May 1975, but these were re-implemented by every subsequent Unix-like operating system up to and including Linux, and they're what you use for I/O and the like interrupts at that level. What about hardware? So, how many people? I just want to see how old you guys are. How many people know what this thing is? No, not a lot of you, maybe 10%. This is what we used to call a computer terminal. Back in the days when computers took up a whole room, we didn't own computers. We didn't have them in our offices at work. We had these terminals, and the terminals talked to the computer via either a modem or a wired connection. And this was the DEC VT100, which was one of the early smart terminals. And what made a terminal smart? Well, you could make characters blink on it. You had arbitrary cursor addressing, so you could sort of jump around the screen and update things, and that allowed you to write games on it. So, smart terminals were really great things in their days. But in order to make this work, you needed special escape sequences to tell the computer, hey, print this over here, make this thing blink. And those escape sequences are defined on this card. So this is essentially an API between programs and the terminal. Once again, it's not clear if it deserves to be called an API, but it certainly feels like one. Another kind of API is between the program and the underlying hardware, but not the processor. So in the IBM PC, and then in all the compatibles that were made thereafter, in order for the program to talk to, once again, to do I/O and to do other sort of interactions with the lower level hardware, but not the processor, they had to do these BIOS calls. The IBM PC was an open architecture, and the BIOS was defined in one chapter of this purple book, the technical reference for the IBM PC. So that's another kind of an API. And what about command line interfaces? So here's the MS-DOS command line interface, which was adapted from the DEC System 10 command line interface beforehand. And it's not exactly an API, but what if you're using a scripting language? These things play exactly the part of method calls in an ordinary programming language. And if you look at the two-part test that we made, it certainly functions as an API. By the way, amusing little prose on the box. You probably can't read it from there, but it says this. It says for computers compatible with IBM personal computers. It's kind of a mouthful, but they were saying something important there. They were basically saying this defines a way to interact with any computer that implements the correct underlying APIs. What about modems. It turns out, so if I said ATDT and then a phone number, how many people, by show of hands, would know what I'm talking about? Wow, many of you. I'm astonished. Anyway, back in the old days, when people had modems, that was how you told them what to dial. And there was a whole sort of little language for communicating with the modem. Initially, you actually typed it on the computer terminal, but eventually computers sent it to the modem. And it turns out that it's still alive today, like in all of our cell phones. It turns out cell phones have two computers in them, the main computer and then the baseband, which handles the radios. And the way the main computer talks to the baseband is through these ATDT codes. So this is an API that has been re-implemented hundreds of thousands of times and long outlived the underlying hardware. What about Adobe PostScript? It is a language, right? There's the language manual for it, but it's also the API that Apple's Macintosh has used to talk to laser writers to basically describe the page that's going to get printed out. So is it an API? Is it a language? Is it both? I don't think there's any easy answer to that question. Honestly, I don't think there's any hard and fast distinction between APIs and languages. Technically, I might describe this as an API that embodies a language. Same thing, by the way, for like Perl regular expressions. It's an API and it's a little language. What about wire level protocols? So SMB, the server message block protocol, which is what Windows uses for printing and file sharing across networks. It was re-implemented by Samba to allow Linux systems to interoperate with Windows systems. Is that an API, wire level protocol? What do you think? Only a few of you think of it as an API, and yet, it is an underlying communication mechanism that allows components to interoperate, but you don't program with it exactly like a traditional API. Finally, in the modern era, we have web APIs. If you've got a web service, in this case, Delicious, you publish an API so that you can sort of mash the things up and build programs that use them. So, we have APIs all the way from the earliest of machines, from the EDSACs of the world to our modern web applications. The Java, was that, did I just discuss the wrong one? Oh, God, sorry, my bad. Yeah, Win32. So basically, this is just another operating system API, bigger operating system, bigger API, but not fundamentally different. And it was re-implemented by by Wine, so that you can program, against the Windows APIs on your Linux machines. Java, once again, just like Fortran and C, it's another set of core language APIs, and it was re-implemented by ClassPath and by Apache Harmony and Android and so forth. And now we get to Delicious, which is just a random web service API, where the APIs are using a different description, they're using JSON or whatever, but they're still APIs. So that brings our tour to an end. What have we learned from the tour? Well, first of all, the two-part test may be too broad. It admits instruction set architectures and command line interfaces, wire level protocols and the like. If we want to take them out, we can amend the definition to say that an API must augment a programming language or calling convention. But more importantly, we learn that APIs come in all shapes and sizes, and they keep getting bigger. Many of them live on forever, often way past when the original hardware for which they were written dies, and that they create entire industries, both above them, where people write programs to the API, like the programs that ran on Windows, and below them, the entire sort of, IBM compatible PC industry was re-implementations of the BIOS and so forth. And that, in summary, APIs are the methods of operation by which components in a system use one another. So they are basically the glue that connects the digital universe. Finally, I would like to conclude with a brief legal digression, though I am not a lawyer. We've always had the freedom to re-implement each other's APIs. In fact, every single API that I just discussed in that whirlwind tour had many significant re-implementations. Here's a little table, which I'm not going to go over now, of all those APIs, who created them, when they were created, an important re-implementation, and the year that that re-implementation took place. Even the EDSAC instruction set architecture was re-implemented. amazingly. You know, it was designed in 1948, and it turns out that a decade later, Toshiba and Tokyo University had a consortium where they built a transistorized version of EDSAC that re-implemented the instruction set architecture so they could use the same library. You know, and they basically copied the entire spec from the book, Wheeler, you know, WWG, and there was no contact between the consortium and Cambridge. Wilkes learned about it later on, and he was thrilled that these guys were able to build a whole new machine just by re-implementing his APIs. But now, and for the last 8 years, API re-implementation is under serious attack. In 2010, Oracle sued Google in federal court in the Northern District of California for re-implementing the Java APIs in Android. They alleged both patent and copyright infringement, and that turns out to be very important. The judge, who is Judge Alsop, the same one whose interrogatory began this talk, he ruled that there had been no patent infringement, but that APIs were not copyrightable, so that, you know, sorry, let me get it right. The jury ruled that there was no patent infringement, and the judge ruled that APIs were not copyrightable. So that was what happened in the first trial. But Oracle appealed the ruling, and because there had been patents mentioned in the original suit, the appeal was handled by the Court of Appeals for the Federal Circuit, CAFC, who are otherwise known as the Patent Court, and they reversed Judge Alsop's ruling in May of 2014, and then in October of that year, Google petitioned the Supreme Court to rehear the case, but the Supreme Court the next year declined to rehear it on the advice of the Solicitor General under Obama, unfortunately. And that kind of caused the case to be remanded to the court in California to decide whether the reimplementation was in fact fair use. And that's exactly what the court decided. In a jury trial, they decided, yes, of course it's fair use to reimplement an API. Then in October of 2016, Oracle appealed that jury verdict, and in June of that year, Stanford and 76 computer scientists and engineers all wrote an amicus brief saying, we've always had the freedom to implement APIs, to re-implement. We need to keep that freedom. But sadly, the court did not listen to that amicus brief, and they ruled, they overturned the jury verdict on fair use. This is unheard of. That never happened. But it did happen in this case. So, right now, it is the law of the land that APIs are copyrightable, and you cannot re-implement them, without the permission of the originator of the APIs. That has not been the case for the past 70 years, but it is the case today. Recently, that is May of this year, Google petitioned for the entire Court of Appeals for the Federal Circuit to rehear the case, and a subset of those 75 scientists and engineers wrote another amicus brief calling for the rehearing. Just in case you're curious, who these people are, they are the designers of these systems and languages. But names you've heard of, Steve Wozniak, and gosh, I don't know. I don't have time to go over the names, but you can look. I have a pointer in the talk to it. Tons of people, that, Gordon Bell, there were like, 10 Turing Award winners in this list. These are the people who believe we have the freedom to re-implement APIs. They're also the authors of these books. Since a bunch of you have studied computer science, you probably have these books on your shelf. So, what does it mean for you if the Federal Circuit ruling stands? It means you cannot re-implement an API without permission from its author. This may require you to pay licensing fees, or they may just say, hey, there are certain restrictions, like, yeah, you can re-implement this API, but you can't do it on a mobile device. That sounds ridiculous, right? But those are exactly the rules that Oracle attempted to apply to the Java APIs. So, this is the future if this ruling stands. And, if you guys think that software patents have caused problems, it turns out that software copyrights will cause much worse problems, because patents are limited to basically 20 years, whereas copyrights grant a near perpetual monopoly on writing and implementation of this little language. And by near perpetual, I mean life plus 70 years if the API was written by a person, or a total of 95 years if it was written by a company. Well, there have only been computers for 70 years. So like, if nobody can re-implement your API for 95 years, it's yours. You've got a monopoly. Do any of you use GNU or a PC or Samba or Wine or Android? Sure you do. Probably you use most of these things. Well, none of them could have been written without, the ability, the freedom to re-implement APIs. So that's the stakes here. The stakes are awfully high. The right to re-implement APIs is crucial. New entrants won't be able to compete against incumbents, and the result will be software that's less interoperable. You'll have silos, and you'll spend less time hacking, more time talking to lawyers, and companies will spend less time building products, and they'll spend more time basically fighting with each other in the court or negotiating. So, in conclusion, APIs date back to the dawn of the computer age. They're the glue that connects the digital universe. The magic of APIs, what makes an API, is the fact that it can be re-implemented. We've been free to do so since the time of EDSAC, and I sincerely hope that we haven't lost this freedom. So what can you personally do to ensure that we don't lose the freedom? Well, consider not developing APIs unless you know they're free to re-implement. Have a chat with your employer. Consider not working for companies that assert copyright on APIs. And finally, make your opinions known to those in power, whether it's executives at the company that you work for, or the courts in amicus briefs, or Congress. So thank you for coming to my talk. Of course, we have no time for questions, but if you have questions for me, ask me anything in whatever it is, 20 minutes. Times Square is the room. It's the 7th floor of this building. Thank you for your patience.